Okay, so this is continuing on with the chapter 13 slides. Last time we talked about the insulin signaling, glucagon signaling in response to blood glucose level, and how if blood glucose level got high, then the GLUT2 transporter would transport glucose into the beta islet cells. The glycolysis would increase the amount of ATP. That ATP would act as a signal to um, close a potassium channel. That change in membrane voltage would cause a regulated release of insulin into the bloodstream. That bloodstream insulin, the insulin would then travel to all of the body wall muscles and be a signal that caused GLUT4 to be inserted into the membrane and cause the uptake of glucose to bring blood glucose level down. So let's move on from uh, the insulin signaling and talk a little bit about um, glycolysis. Um, Glycolysis is probably the oldest um, uh, utilization of sugar for ATP generation, and the reason I say that it is the oldest is because there's not a single cell on the planet that doesn't do glycolysis. And so, because it's the same or very, very similar for every cell on the planet, it must be evolutionarily very old. It occurs in the cytosol. Glycolysis always occurs in the cytosol. Um, and it's going to, excuse me, break down glucose, a six carbon chain, into pyruvate, a three carbon chain. And so, um, in doing so, it is going to generate uh, uh, two ATPs more than it used. So it's going to use two ATPs, generate four ATPs, and thereby have a net gain of two ATPs. It's also going to have a net gain of two NADHs. So, so is this a catabolic or anabolic process? This is a catabolic process. We are breaking down glucose to make um, uh, smaller three carbon chains. So this is a catabolic process. Um, Glycolysis is an anaerobic process, um, does not require any oxygen. The requirement for oxygen for your body cells um, is uh, that oxygen is the final electron acceptor of the electron transport chain, which is in the mitochondria. So that's further downstream than glycolysis. So glycolysis is an anaerobic process. Um, so when we break down sugar, um, we're going to do it in many steps. And there's a reason for that. By breaking down into many steps and having all those energies put into an activated carrier molecules, less of it is lost as heat. And so if we were just to burn sugar to make CO2 and water um, in one step, we would lose most of the energy as heat. Whereas if we do it in many small steps, we can get a lot more of the energy out of of the process. So stepwise oxidation of sugar in the cells allows us to have a much more efficient process. Um, Glycolysis is central to producing ATP. Um, it's not just the first step, but it, even the byproducts are going to be utilized in subsequent ATP production. So so in step 6 we're going to produce NADH, and then in step 10 we're going to produce pyruvate. And so we are going to produce a couple of ATPs, but those are going to be inconsequential in comparison with the energy that we get out of NADH. And then those pyruvates are going to produce more NADH as well as FADH2 in the TCA, or the citric acid cycle, or the Krebs cycle, or whatever you're calling it. And so glycolysis being the first step to producing those NADHs and FADH2 is central. It's a very important step. Um, so sugar as well as fat, all roads lead to acetyl-CoA. So sugar being broken down into glucose into pyruvate, and then that pyruvate moving into the mitochondria and becoming acetyl-CoA, or fatty acids being broken down and becoming acetyl-CoA, or proteins being broken down and acetyl-CoA. All roads go through vinegar. Okay, so so one of the central questions is what about if we don't have oxygen? Many bacteria are anaerobic. Um, Yeast can be anaerobic. Um, your cells can still do glycolysis if uh, if they are in anaerobic conditions. So what are we going to do? Well, because the NAD is the uh, is required for the uh, one of the steps of glycolysis. It is it is an oxidizing agent. It has to become reduced. Um, Once you have that NADH, you don't have that NAD anymore. And so glycolysis won't be able to continue until you can get that NAD back. So how are we going to oxidize the NADH to get the NAD back so it can be the oxidizing agent? Well, we can take that reduced form and use it, and the pyruvate, which was the downstream um, product of glycolysis, and we can do fermentation reactions and get that NAD back so that we can continue to get those 2 ATPs. That's what bacteria do. That's what yeast do. They do fermentation reactions. And you do too when you're in anaerobic conditions. So what is fermentation? Well, in your cells, as well as in many bacterial cells, um, because we have to recover that NAD for glycolysis, we can take that pyruvate and use NADH a um, as a uh, oxidizing reagent, so so or reducing agent. I'm sorry, um, and so then the NADH will become NAD again. Um, so so when NADH is acting as a reducing agent, it becomes oxidized, and we recover that NAD. And what is it going to act as a reducing agent on? Those pyruvates that we generated. So now we take that pyruvate, turn it to lactate, and recover our NAD. That's how our cells do it, and many bacterial cells do it, and so we're going to produce lactic acid. There's another kind of fermentation, and that is the ethanol fermentation. Here it's a two-step process, again, to recover the NAD, and the byproduct of it, instead of being lactate, is going to be ethanol. So that's fermentation, and that's the reason for fermentation, is to recover that NAD so we can have subsequent steps of glycolysis. Okay, so that's it for chapter 13. You can move on to